Hello, welcome to this presentation of IoT Network Security using NFC. This presentation reviews a paper that Abhijit Chitnis and I, Bill Dockery, wrote for the summer 2019 Introduction to Operating Systems class at NYU as part of our master's degree curriculum. What we'll cover today is our alternative to the Wi-Fi organization strategy for connecting devices to Wi-Fi. It's called EasyConnect. We feel there's an inherent flaw in the design and that we've improved the method from a security and even IoT product/production design. So we'll overview the EasyConnect strategy before describing the alternative and give some evidence to support our claims. We'll even talk a bit about where we think we could go further with the alternative, and there's a slide at the end for questions, but of course this is recorded, so if you do watch this and have questions, please drop us an email with the addresses here on the title page. Our primary motivation in changing the EasyConnect model is the lack of authenticity in IoT communications. The CIA triad is obviously our foundation, for you do need to know that a conversation between two hosts is not being listened into, confidentiality, that the integrity of that communication, a packet sent, is the packet received, is still very valid, and the availability to be sure that you can even have the conversation. But can you really trust that the packets are always coming from the intended device? This should send shivers up your spine when you consider the potential for chaos in many industrial, medical, and even household contexts. For one example is your refrigerator talking to a grocer. What if someone was to assert themselves and order you 5 gallons of milk versus the one that you truly need? This could be even greater catastrophe when this happens in environmental monitoring systems in industrial settings. And part of the reason for this being so problematic is that PKI for IoT is risky and complex. Relying on third parties for proof of trust relies on communication models that create plenty of opportunities for things to go awry and other persons asserting themselves. Now, in another situation where it's not so much the assertion of an attacker in there is the session key setup. Data itself has a shelf life. So just trying to get the packet from the IoT, the measurement, the reading, over to a centralized system for analysis can itself be troublesome if the protocol takes too long for itself just to set up. Just to have someone pick up the line on the other end and note that the IoT is sending the packet. And we hope to change this in our model. We do highlight one recent attack on the bottom just to give a true real-life example, make this real for you, is a trivial bug that turned a home security camera into a listening port. And on this slide, we highlight 5 more real cases of where IoT itself has been part of an attack or itself been attacked. The Stuxnet up top being probably the most famous of all the industrial settings where PLCs were used to sabotage uranium enrichment facility. Down at the bottom where a university itself was being hacked and a great number of hosts there were creating all sorts of availability issues and mirrored a little bit of chaos. The gist here is to understand that IoT itself has become a target to create botnets so that great chaos could be made in all the CIA triad. And potentially one reason for this is the lack of availability or a secure way or an assured way to update the IoT. And in our strategy of what we're going to show you in a bit is an opportunity to make things a little easier for IoT to trust even the patches that come down to it, potentially even run a network operating system on the fly, and in a sense, keep these devices in a much more secure state simply by the update to their code. Now, what others have done, what we're highlighting here is the EasyConnect model, and what the Wi-Fi organization is suggesting is the use of PKI as the foundation to implement the CIA plus authenticity, digital signing, for connecting to the network. It's based on the use of a configurator acting as a middleman to take information from an enrollee. In the case of taking it from the enrollee, it's typically a factory asserted private and public key and registering that with a centralized device. There's also a bootstrapping process that equates to a number of handshakes and protocol exchanges to get the device on the network and recognized by the centralized services. Although much of the EasyConnect model is using various secure methods to talk between the end nodes and the configurator, there are inherent flaws, and we feel first that devices should not be allowed onto the network unless authenticated. This means that network access control could be done via a pre-shared key that's asserted at the time of things happening. And that in itself is the big benefit there, because in EasyConnect, these pre-configured keys are static and usually displayed with a QR code. The reverse should happen. The device should accept the key dynamically on factory reset. That way the device cannot be spoofed if the key is asserted shortly after being collected from a central device and asserted onto the end node IoT. Additionally, we do not need the asymmetric keys at first. The primary goal in any session is get to a symmetric key, so why not pre-share this? We are making some assumptions. It would be nice that IoT should be talking to only one device and preferably unidirectionally, although we have not ruled out the bidirectional communications between the end node and the centralized service. We do believe that symmetric session keys can rotate continually once established, so we can get perfect forward security in this as well. If the session key is a pre-shared key, then we don't need the lengthy PKI and RSA exchanges and can send packets asynchronously. In other words, we can discover that we may be able to avoid TCP handshake and deliver closer to real-time measurements from IoT. Now, removing these protocols leads to a smaller OS, fewer, stronger encryption algorithms, potential for a smaller processor, and even potentially smaller memory. What we're really proud of is that the PKI-CA in this scenario is not necessary. If we've already built the trust, it should be just as easily to rely on self-sign asymmetric keys, and that's if digital signatures are still considered necessary in special use cases. Here's a diagram to explain how the process works. We do use a configurator, but it collects a key to assert to the end device from the centralized service, and therein lies the difference that the key could not be spoofed as most pre-configured factory could, especially with QR codes. It does not require a true network connection to assert or verify as well. In other words, no PKI. The IoT should be coded to accept this basic key via NFC one-time at base configuration, a la factory reset. There's very small chance of capture by a malicious attacker. We could secure the NFC transmission itself, but it's really proximal, and unless someone's literally there to get it, it's not going to be noticed by anyone. This key or even a hash could be used in NAC to assert permission to join the network. An example of the 802.1x pre-admission condition. The central system acting as the authentication service that supports the network authenticator at request. In other words, the network can go out to the centralized service and validate the credential that was presented by the IoT to say this is truly a device that should be allowed onto the network. Once on the network, the device reports home to the centralized service and can establish a new symmetric key. Supporting asymmetric keys receive updates or even the running operating system itself, etc. A setup to test this theory is detailed here on slide 8. Although a great number of variants could be used, the basics are two end nodes and a configurator. The logic here is that even in, and maybe especially in, industrial settings, we have physical access to the IoT. The centralized service may or may not be physically available, but that device is more functional than the IoT itself. The initial symmetric key can be collected by the configurator by many different means. For example, the traditional web access is through any other SSL type session. The proof to our design from a security point of view is supported by the statement that complexity is the enemy of security. We remove a lot of the moving parts by eliminating the external CA, no need for PKI, but still have encryption, reduce traffic, handshakes which are themselves a protocol, and every protocol has frailties. We also have the potential to remove a need for Wi-Fi. Why not do things over Ethernet over power, as most IoT is actually embedded in devices that are powered or themselves are powered. The fact that the device is not allowed onto your network prior to being configured securely is an excellent situation where we want to keep closed networks secure and closed, especially in industrial settings. The bootstrapping processes do not need to be large and can actually support a network-based OS load. For example, a basic EEPROM might be all that's necessary to collect the basic config and symmetric key. The fit-for-purpose protocols for setup can be made proprietary and make it harder for attackers to keep up, and the need for non-volatile storage may be eliminated due to the use of operating systems being loaded over the network, but it's more likely that it could be reduced at least in size. Memory and processor can be reduced because we're not going to use the same number of encryption algorithms or more efficient ones, or even have to store 8 where maybe 2 are necessary. Where power is available, again, with embedded IoT or with IoT with power cord, we could just as easily use the power as connectivity and remove the need to deploy Wi-Fi hardware. Cheaper devices all around. Here we have a view of the potential impacts of reducing the CPU and storage on devices. Price for a CPU. The more performant a device is, the more likely it is to be of higher value, the more likely for theft. And on the right here, the price for memory capacity. The less memory, the less storage you need to put in things, the smaller the physical size, and again, lower the cost in general. Let's end with a note that we did not cover all the advantages of this model, but also take a moment to note that we can enhance, as next steps in research, to using localized addressing in gateways, in other words, a proxy or an API gateway to enhance the security of the IoT. When we do with things like IPv6 in the future, where every address is actually reachable from anywhere else in the world, we definitely want to get the obfuscation back that we relied upon within the RFC 1918 type addressing in IPv4. We also would like to remove a barrier to real-time monitoring by establishing the trust via the asserted symmetric key and allowing for a reduction in handshakes and communications overhead if we rely on UDP-based transmissions without higher layer handshakes as well. Again, with trust established through these shared keys via a configurator versus through protocols, well, the session itself can be reestablished, reconfirmed through a new key at greater intervals than every single time that a communication is made. The fewer packets leads to less power consumption, less traffic on our network. Again, hopefully through an API gateway or such can actually be batched and sent in greater packets at the time of release and not stored on the IoT itself. These are just many of the few areas that we can go to post this exercise. And lastly, we have our page for questions. So I'll leave you with thank you again for sharing your time with us to understand our proposal for IoT network security using NFC, and we hope to see you in our email inbox.